Hi grade 11s. Now we move on to a separate type of subtopic of trig, which is called 2D trigonometry, and it's all about trig in triangles. Now we're going to start off with a revision of grade 10, and then we're going to move into some really exciting trig, and ultimately every single exam from now onward will always have one question which is on trig in triangles. So this first topic, one of grade 10 revision, you might remember from grade 10 is that we only ever used trig in right-angled triangles. Now, this is really important, except not every triangle is right-angled. And so after we do this, we want to push trig into every triangle. And so there's really some exciting rules that we study in grade 11. The sad thing is that often once we've studied those rules, we forget about our basic sine, cos, and tan in right-angled triangles. And this is actually really, really useful. So let's have a look. If I have a right-angled triangle, most importantly, you have an angle of theta, and every side in the triangle can be labeled according to theta. So this would be the opposite side, this would be the adjacent side, and this would be the hypotenuse. Now, to be honest, I always label the hypotenuse first, because otherwise you could be confused by thinking that the hypotenuse is also adjacent to theta. And so I always label my hypotenuse first and then my opposite and adjacent. Now, very, very importantly, these definitions of sine, cos, and tan are only true in right-angled triangles. So when we push into the next topics, which are all about every type of triangle, we have to remember that the basic definition of sine, cos, and tan is only true when you have an hypotenuse, which is only in right-angled triangles. So what is the definition of sine? Well, we probably remember that sine is opposite over hypotenuse, cos is adjacent over hypotenuse, and tan is opposite over adjacent. Now, I think I've said this before, some people remember SOHCAHTOA, which is, I've said this before for sure, I can't remember how to spell SOHCAHTOA, and so it doesn't help me. SOHCAHTOA doesn't help me at all because I just can't spell it. But if you remember that, it's a bit of an acronym. It basically stands for sine is opposite over hypotenuse, cos is adjacent over hypotenuse, and tan is opposite over adjacent. Now, I can't remember that. So what I do remember is I remember silly old hens cackle and howl till old age. So that's the kind of little word, I'm sure there's a word for it in English, that I think is mnemonic. I don't know English very well. That's what I remember in order to remember these definitions. And so there's my memory aid that will help me, and I actually have remembered that it's called a mnemonic, which is basically just a memory aid to try and help you remember that. So silly old hens cackle and howl till old age. So sometimes that's how I choose to remember this. Now, I think the most important thing that I'm going to say is don't forget that this is only true in right-angled triangles. So the moment we get to any question, the first thing I do is I highlight my right-angled triangles. Okay, so let's look at some examples. Example number 1. First of all, is it a right-angled triangle? Absolutely, which means all your usual trig applies. So basically, they've told me that CB is 12, we've got an angle of 44, and they want us to determine the other two sides of the triangle. Now, don't forget, if you've got 44, this third angle in the triangle, you can always figure out because of sum of angles in the triangle. Now, I only do that if I actually need it. Otherwise, I have to write down a whole bunch of stuff I don't want. So this is opposite. I always like to label in my hypotenuse, which means this is adjacent. So the first thing I do is ask myself, if I'm looking for the side of AB, AB means I'm looking for the adjacent side. Now the only side I know is this hypotenuse, and so I clearly need to choose a trig ratio that involves adjacent and hypotenuse. And adjacent and hypotenuse is cos. So therefore cos of 44 would be the adjacent side, which is AB, over the hypotenuse, which is 12. So I pick up my calculator and I'm basically multiplying by 12 on both sides. So cos 44, and I'm multiplying by 12 on both sides. So that 12 cancels, multiply by 12 on that side, and you simply do it on your calculator. You don't have to show that multiply by 12 or anything. Just pick up your calculator, and because this is the answer, I can round it off to 2 decimal places. So literally it's 2 lines of working. Now I'm looking for CA. Now CA is this side here, which is the opposite. Now I actually have now figured out the adjacent. So I can use opposite over adjacent, which would be tan, or I could use opposite over hypotenuse, which would be sine, or I could use Pythagoras' theorem. Now I try and avoid using a side that I've just found out, because if I've made a mistake, then I carry my mistake through. Also, this 8,63 is rounded off. And so if I use it, I'm technically going to get a rounding error. Now, I wouldn't penalize that in a test because there's nothing wrong with using AB. That was an answer that you've gotten and you're allowed to round it off. So there's lots of options here. Personally, I would use sine, simply because I have no rounding and I'm simply using the sides that I was given. So sine is opposite, which is CA, over hypotenuse, which is 12. So in exactly the same way, I would multiply by 12 on both sides. And because this is an answer, I can round it off to 2 decimal places. Don't forget that you only ever round off the answers. So this is 8,34. But you could have done Pythagoras and you could have used tan. So whatever works for you. You might have got a slightly different answer if you used if you used Pythagoras and tan, but it would have been marked absolutely correct. The difference would have come from the rounding of that AB. Right, let's move on to another example. Next example says in the diagram below, AD is 13, you've got DCB, which is 31, and we need to determine a whole bunch of lengths. Now the first thing I would do is I would highlight my right angle triangles, because so far I can only do trig in right angle triangles. So triangle DBC is right angled, and then the big triangle of CAB is right angled. So there's 2 different triangles that I could work in here. So let's look at what they ask us. They ask us for DB. Now DB is part of the little triangle, and if I labeled the triangle according to 31 degrees, this would be my opposite, this would be my hypotenuse, which would make this side adjacent. So I'm actually looking for the opposite side, so this is opposite, and the only other information I know in that triangle, remember you can't use 2 unknowns, so if I'm looking for opposite, I need to use something I know. Now I know that 15 is the value of CB, and so that's A. So I'm looking for the trig ratio that involves opposite and adjacent, which is tan. So I know that tan of 31 degrees would be opposite, which is DB, over adjacent, which is 15. So I'm going to multiply by 15 on both sides, and that cancels away, and I can round this off because this is the answer. It's 9,01. So often what I go and do is actually label that in. So this is 9,01, because I might need it in a subsequent question. Right, let's look at the next one. The next one asks for DC, which is the hypotenuse in that yellow triangle. Now again, lots of options. I could use Pythagoras. I try and avoid Pythagoras because I find it a little bit annoying. If I'm trying to find hypotenuse, I actually now have the opposite and the adjacent. So I could use sine or cos. I would prefer to use cos in this instance, simply because I have the adjacent side. The adjacent side is 15. Remember, it's adjacent to 31. So cos of 31 would be adjacent over hypotenuse, which is DC. Now this is a little bit more annoying to solve because you're solving for a denominator. So what I'm going to do is I'm going to multiply by DC on both sides so that it stops being at the bottom, which means I get DC times cos of 31 degrees equals 15. Now what I need to do is I need to divide by cos 31 on both sides so that I get my DC by itself. And so I'm going to pick up my calculator and simply say 15 divided by cos 31. So I get a DC value, and I can round this off. I get 17,499, so 17,50 or 17,5. Now, as I've said before, you could have used sine and you could have used Pythagoras, and you probably would have maybe got slightly different rounding, but it would have been marked right either way. Right, on to the next one, AC. Now AC is part of the green triangle, so that's a whole long thing there. The only problem is I have no angles in AC because I don't have an angle here. And it doesn't look like I can work out that angle because I don't know this angle at C. And so I'm a bit stuck in terms of angles. But don't forget that angles are not the only thing I know in right angle triangles. I also know Pythagoras. So at the moment, I know this length, which is 15 of CB, and I actually know this entire length of AB because I can add my two parts together. And so I think I can find AC using Pythagoras' theorem. So Pythagoras' theorem says that AC squared, the hypotenuse squared, would be equal to AB squared plus CB squared. Now don't forget, the moment you use Pythagoras' theorem, you have to credit him and write Pythagoras in brackets. Now you could have gone straight to the substitution step. So you could have said that AC squared equals, now I need to add 13 and 9.01, so that's 22,01. And now that's a rounded off version, but this is allowed because it's a new question. Now you don't have to show any working from here. You could just go 22.01 squared plus 15 squared, and you could square root that immediately. If you want to show a bit more working for your notes, I get 709,4401, and then I would square root both sides. And so when I square root, don't forget your hypotenuse has to be the longest distance, so you'll know you're wrong if it's not longer, but I get 26,64. Now again, I'd probably write that in because it might be useful to me in the long run. Right, so far so good. Next thing it asks for is angle A. Now angle A is exactly what I said I didn't know. Now now that I have lots of information from that triangle, I can find angle A because this is my hypotenuse in my big triangle. Don't forget I'm working in my big triangle because it's right angled, my green one. This is opposite, which is 15, and adjacent is that whole long 22.01. So basically I can use cos because I'm looking for, I can actually use any ratio. I could have used sine, cos or tan and then work backwards to my angle. So it doesn't really matter which one. I'm going to pick sine. Why not? So sine would be 15, so sine of angle A would be the opposite, which is 15, divided by the hypotenuse, which is 26,64. And don't forget, you just put that 15 divided by 26.64 into your calculator, and then you get an answer, and you do shift sine of that. And you don't have to worry about a second solution because this is an acute angle. So you will simply get A is 34,267, so 0.27 degrees. Now if you used cos or if you used tan, you'd probably get something slightly different because of the roundings of the different sides, and that's absolutely fine. The person marking will just mark whatever method you choose. And now they've asked for ACD. Now ACD is this angle here up top. I don't even know if I'm circling this enough. There's ACD. Now that's not part of a right angle triangle. However, if I can find the entire angle, which is ACB with the 31, I can take away the 31. Now of course I could go about using my trig now, but I have just found that this angle over here is 34.27. So don't forget sum of angles in a triangle, because now I have 90 degrees at B and I have 34,47 in the corner. So I basically have a triangle that looks like this. I have a right angle triangle, I have 34,27. Can I find the whole angle there? So that would be called ACB because that's the big triangle. So I would say ACB, and I wouldn't show any working at all. I would just use my calculator, and 180 minus 90 minus 34.27 gives me 55,73 degrees. And my reason, don't forget that this is geometry involved in this trig, so sum of angles in triangle. And therefore ACD is a part of that because that divided down to D there, and this is 31. So I can minus 31. I don't have to explain that. I just take away 31 and I get 24,73 degrees is what I wanted. Great, so a lovely question of mix of trig ratios, solving for sides, solving for angles, a bit of Pythagoras, sum of angles in a triangle. Really nice question to pretty much revise everything. Okay, last one in this revision section. In the diagram, BA is 25, we've got 41 degrees and 12 degrees. Determine the length of CD. Now again, always highlight your right angle triangles. So there's two here. There's CBA, which is that one, and there's DBA. A, which is the big one. So I can only use trig in those two triangles. Now what's my plan? I like to always have a plan. Now I can't get DC directly because it's not part of a right angle triangle, but could I find DB and then subtract CB, because both of those are sides in right angle triangles, and that'll give me the value of DC. Right, so let's go about finding DB first. So my whole angle there would be 53 degrees, and this would be my hypotenuse, would be DA. Opposite would be the DB, and this would be adjacent. Now that means I've got my adjacent side and I'm looking for my opposite side. And so opposite and adjacent would be a ratio of tan. So tan of my 53 degrees, because it's the full angle over there, would be equal to opposite, which I don't know, that is BD, over adjacent, which is 25. So I simply multiply by 25 on both sides, and now this value of BD I'm not going to round off, because this is not the answer to the question. I'm going to use this is a stepping stone, and the moment something's a stepping stone, I need to keep at least 4 decimal places, because the rounding might be affected in the long run. Right, now I'm almost going to follow exactly the same idea, except it's with 41 degrees, because with 41 I'm still looking for opposite. This is my hypotenuse, and this is still my adjacent. So I'm almost going to repeat exactly this calculation, except with tan of 41, which equals CB over 25. So multiply by 25 on both sides, and I get CB is 21,73216. At least 4 decimal places is good. And then finally, I can say that's great. CD would be equal to your whole distance, your BD, which is 33,1761, and I'm going to subtract that CB, which is 21,73216, and that gives me a value of 11,44. So really nice again. I think it's key to focus on the fact of highlighting your right angle triangles, and at the moment only doing trig within those. Of course we're going to expand on that, and that's the fun part.